If you recall from chapter 3, we were actually looking at representation of particles, and we said we use a chemical formula to represent particles. All right, so we use a chemical formula to represent particles. For example, when we look at water, we write it as H2O. We use the symbol for hydrogen. We use a subscript of 2 indicating that there are 2 hydrogen atoms in a water molecule. We use the symbol for oxygen, and the 1 is usually implied. If there's only one of it, we don't write it. So the way we represent compounds is using these formulas. Now for molecular compounds, we call it a molecule, and for ionic compounds, we call it a formula unit. So the formula unit for table salt is NaCl. And this says that we have 1-to-1 ratio. Carbon dioxide, we got 1 carbon to oxygen, 1-to-2 ratio. Table sugar, sucrose, C12H22O11. In other words, we have 12 carbon to 22 hydrogen and 11 oxygen. Keep in mind, these subscripts right there indicate in the chemical formula the ratio of that element within the compound. So it's a relative ratio that we see. Okay, those are the relative numbers within the compound. And we have to be very careful when we're dealing with molecular compounds or ionic compounds. We do not touch these ratios, because even changing it very slightly will give you a completely different compound. Let's take, for example, the difference between CO and CO2. This is carbon monoxide and this is carbon dioxide. Carbon dioxide does not kill you in high concentration. Okay? But if you're exposed to high concentration of carbon monoxide, good luck. So that ratio has to be maintained because it gives us different types of compounds. And the way we write the formula matters as well. The chemical formula lists the most metallic element first. So when we say metal, if you guys recall, on the periodic table, we have the metals on the left side of the periodic table, non-metals on the right side. So if I have an ionic compound, usually it's between a metal and non-metal. And we'll talk about the difference between ionic and molecular in a little bit. But for now, the rule of thumb is as follows. You always start left to right, bottom to top when you're writing things. Okay, so if we have a compound made out of sodium and chlorine, we write it as NaCl, not ClNa. Okay, so take a look. Na is right here, whereas Cl is all the way to the right. That means we write Na first, then Cl. This is if we have a metal and non-metal. But what if we have that rule apply if you're going with non-metals as well? So take a look right here, nitrogen and oxygen. Nitrogen is to the left of oxygen. So if I have a compound between nitrogen and oxygen, whether it's NO and O2, we write it as NO2 and NON, not O2 and NON. The same if I have a compound between sulfur and oxygen. It's SO2, not O2S, because sulfur is below oxygen. Okay, so again, the rule is left or below always goes first. We can also take it a step further. If you look at the element that are listed in table 5.1, they are in order of their appearance in a chemical formula. So we always start with carbon, followed by phosphorus, nitrogen, hydrogen, sulfur, iodine, bromine, chlorine, oxygen, and then fluorine. So you should know, you should familiarize yourself with that order. And of course, there are few exceptions to this. It doesn't always work that way, and those are due to historical region. For example, when we write the hydroxide ion, we write the oxygen before the hydrogen. But when water, we wrote it first, right? H2O. But in here, this is for historical reason. They always wrote it that way, and they continue on doing so. All right, let's take a look at some practice. So go ahead and pause the video and see if you can answer these based on what we just learned. Then come back and check your answer. So this one says I have 4 oxide, that's oxygen ion, 4 oxide ions, and 3 iron ions. So iron is a metal, so it should go first. So it's Fe3O4. That would be our formula, Fe3O4. Acetone, on the other hand, contains 6 hydrogen, 3 carbon, and 1 oxygen. So carbon goes first, followed by hydrogen, then oxygen. So that would be C3H6O. In addition, some compounds are going to contain polyatomic ions. And we have to be careful with those polyatomic ions. In this case, we have magnesium nitrate. In magnesium nitrate, I have 2 nitrate ion, and don't worry about what that polyatomic ion is. Just focus on the use of parentheses here. So for this one, since magnesium has 2 plus charge, nitrate has negative, I need 2 of them, so I need 2. So I put parentheses around nitrate in order to use that subscript of 2 right here. Okay, so that subscript of 2 is needed in order to indicate that I have 2 of the nitrate, all of it as a whole. So that nitrate as a whole will lead to the following. If we were to count how many atoms we have of each, we're going to have to use what's inside the parentheses and multiply it by that too. All right, so let's take a look what we have here. We have the symbol for magnesium. We're not using 1 because we only have 1 to indicate 1, so it's implied. Inside the parentheses, we have the nitrate ion, so let's focus on that first, then we'll go out. This is the symbol for the nitrate group, NO3 minus. Notice the compound itself doesn't have any charges, but we'll talk about that in a bit. The 1 for nitrogen is implied, so I have only 1 nitrogen. Then I have a subscript of 3 for oxygen. That means I have 3 of them per nitrate group. Then after the parentheses, I have a subscript for the whole nitrate group. That too indicates I have 2 nitrate groups. In other words, I have 6 oxygen. Since that 3 times 2 will give me 6 oxygen, I have 2 times 1 nitrogen, 2 nitrogen total, and 1 magnesium. All right, now your turn. Go ahead and determine the total number of atoms or ion in 1 formula unit of each of the following. And go ahead and pause the video, determine it, then come back and check. So in this case, we have 1 magnesium. 2 times 2 will give me 4 carbon. 2 times 3 will give me 6 hydrogen. And 2 times 4 will give me 4 oxygen. If I add them up, I come up with a total of 15. Now let's look at the second one right here. I have 2 mercury atoms here. Times 3 will give me 6 mercuries. 2 times 1 for phosphorus, that's 2. 2 times 4 will give me 8 oxygen. So that'll be 6 mercury, 2 phosphate, and 8 oxygen, a total of 16. Now in the last chapter, or not the last one, the one before, in chapter 3, is it 3 or 4? All right, in the previously, we classified matter. Yes, in chapter 3, we classified matter based on its state as well as its composition. And when we classified it on its composition, we said one of it is going to be a pure substance, right? And the other one is going to be a mixture. But if we were to look at pure substances, we ended up with elements and compounds. But we can further subclassify elements and compounds. Now, if the element is made out of only a single atom in nature as their basic unit, then we call it atomic. For example, neon exists in nature as Ne. That's a single atom. That's as its basic unit. Whereas oxygen gas exists in nature as O2. It does not exist as O. Therefore, it is molecular. So if you have two or more atoms, then it's molecular as the representation as a basic unit. Now, on the other hand, when we come to compounds, compounds can be further subclassified into either molecular or ionic. And that would be based on the type of the makeup of the compound. If the compound is made out of cation and anion, then it's ionic, such as sodium chloride, NaCl. But if the compound is made out of nonmetals, then it's molecular through covalent bonding, not transfer of electrons to create charged species like we have in sodium chloride, but rather through sharing of electrons like we have in water. Okay, so you need to know that subclassification of elements and compounds. As I said earlier, atomic elements exist in nature with a single atom as their basic unit. On the other hand, molecular elements do not exist with a single atom as their basic unit. Instead, they exist in a higher order. Okay, there are a lot of them exist as diatomic, but some exist as more than just diatomic molecules. Okay, some more than just diatomic molecules. And there are 7 diatomic molecules that we require you to know. So anytime you write this in a chemical equation, you're going to write them as such. That would be hydrogen as H2, nitrogen as N2, oxygen as O2, fluorine F2, Cl2, Br2, and I2. You should memorize those as they exist like that in nature. In addition to the 7 diatomic molecules, there are 2 more that exist as such, as molecules rather than atomic. That would be for sulfur, it's S8, and for phosphorus, it's P4. All right, so you should know those as well. That's for elements. Now for compounds, as we said earlier, they could be molecular or ionic. Molecular compounds, they're formed mostly of nonmetals. There are very few that they contain metals, but beyond the scope of this class. As a matter of fact, the only one that I would like you to know is going to be beryllium. Beryllium is capable of forming a covalent compound, and it's molecular. So if you get BeCl2, for example, that is molecular. But anything else, you don't need to know. Ionic compounds, on the other hand, they're made out of cations and anions. Now, in most cases, the cations are metals. Of course, there are other cases where you have polyatomic ions that are cations, but in most cases, they're metals, and the anions are non-metals. All right, so if we look at some example of this, a molecular compound such as carbon dioxide, if you lower its temperature low enough, it will form dry ice. Okay, so the basic molecule for it is CO2. Whereas for table salt, NaCl, it's made out of the cation sodium and the anion chloride. It has a formula unit rather than a molecule. And the difference between covalent and ionic, in ionic compound, a crystal lattice is formed where you have alternating position between positive and negative in order to maximize interaction and minimize repulsion. As a result, you end up with what's known as a crystal lattice. This, you know, that if you actually zoom in on table salt, it actually forms crystals. It's a crystalline structure that forms with this. So for ionic compounds, we learned in the last chapter, in chapter 4, that metal have the tendency to lose electrons in order to have a valence shell similar to the noble gases. And when they do, they don't just lose the electrons into the void, they transfer those electrons. And these electrons get accepted and gained by nonmetals. Okay, so those have the tendency to gain. So you end up with a species that is willing to give up electrons and species that want to accept those electrons. They come together and a transfer of electrons occur between metal and non-metal. As a result, we end up with charged species that get extremely attracted to each other because of the existence of opposite charge. Okay, this type of interaction is called electrostatic interaction. It's highly stabilizing. And we call those types of compound ionic, and the smallest representation unit of these compounds is called a formula unit. And again, as I showed you earlier, they do not have individual molecules, but rather we get this crystalline lattice that maximizes interaction and minimizes repulsion by alternating positions. So even though, for example, if you look at sodium chloride, even though the formula says NaCl 1:1, but in reality, if you were to zoom in at this crystal lattice right here, you would see that every sodium ion is interacting with 6 chloride ion. And every chloride ion is interacting with 6 sodium ion. But we always simplify it to write it as such. We don't do that for molecular compound because that's not the same scenario. Now, from chapter 4, we learned how to predict what the charge is going to be for metals and non-metals for the main group elements based on their position on the periodic table. So you should review that because you're going to need this for this chapter. Now, since ionic compounds are made out of cations and anions, oppositely charged species, and we know that matter exists in nature as a neutral species made out of charged species, right? So therefore, because it's neutral, that means the sum of the positive with the negative must equal each other. They must cancel out and they must equal each other. Okay? So positive and negative charges must equal each other in order to give us that neutrality of matter. Okay? So let's take a look how we can take advantage of that. So let's say I want to form a compound between lithium and iodine. Lithium have the tendency to lose 1 electron. Iodine has the tendency to gain 1 electron. So I end up with the following lithium ion and iodide ion. Plus, minus. So if I were to look at this, plus 1 minus 1 equals 0. Perfect. That means it's 1:1. So it's lithium iodide, Lii. That's how we come up with write-in formulas for ionic compound. Now the next one, calcium, 2 plus, 2 minus. So if I put plus 2 minus 2, I end up with 0. Then the formula is calcium oxide. Now notice I'm neglecting to put 1 and 1, multiplying by 1 and 1. And you'll see what I mean in a second. For aluminum and the nitride ion, we have plus 3 minus 3, we get 0, so it's aluminum nitride. But when it comes to magnesium and chloride, magnesium is 2 plus charge and the chloride is minus right here. In order for it to be 0, I'm going to need 2 chloride. So the way we write it is going to be 1 times plus 2, that's the first one, plus 2 times minus 1. That's the charge on the second one. So I need 2 of them. So therefore, the formula will be MgCl2. All right? That's the formula. Now you can do it that way, or there's an alternative way of writing these ionic compounds. You can simply write the symbols for each with their charges. Okay, so if I want to do it for aluminum ion with an oxygen, with an oxide ion, Then I can write ALO. Okay, let me see if I can show you how we go with this. Okay, so let's say I have Al3 plus with O2 minus. So I write it as ALO. Then what I'm gonna do, I'm gonna take, let me change the color here. I'm gonna take the charge. I'm gonna take the magnitude of the charge from aluminum, and I'm gonna make that the subscript for oxygen. Then I'm gonna take the magnitude of the charge for the oxide ion, and I'm gonna make that the subscript for aluminum. So as a result, I end up with Al2O3. That's how you can come up with a formula. Let's take a look how we can do that for magnesium oxide. So notice the magnitude of the charge is 2 here and 2 there, so I can put them Mg2O2. But wait, for ionic compounds, we always write it as the lowest possible ratio. So what we should be doing instead is actually writing this formula as Mg. That's the correct formula, not this. All right, so the correct formula for it is MgO. Go ahead and try the following. Those are the given the names of the elements or the ions in here. And I would like you to see if you can come up with the correct formula for between these ions. So pause the video, work on this, then come back and check your answer. So we have a potassium ion, potassium, K+, it has 1 charge. And the nitride ion is 3 negative. We want the charges to be equal. That means I need to multiply K with 3, 3K with 300, so the formula will be K3N. Now with the calcium ion, it's 2 plus. And the bromide is just -1, so it's going to be CaBr2. Aluminum is 3 plus, oxide is 2 negative, so we end up with Al2O3.